partial fractions technique. So last time we basically talked about when you had distinct linear factors, how to set up and find the constants to break it down into so that you could actually get two simpler fractions that you could integrate. So we're going to look at a couple more cases here. All of the ones we've seen so far had distinct linear factors, so they are all different ones. So the case 2 we're going to start with today is a product also of linear factors, but some of them are repeated. So not all distinct, some of them are going to be repeated. If that's the case, then this is how we can kind of write it here if we have our R of x over Q of x. Okay. And then the repeated linear factors would be listed as the following. So the repeated linear factors could be written as, they can be broken down into smaller pieces by doing the following. So you would take A over whatever factor that was, first to the first power. Then you would need to set up another fraction to the second power, and so on. So whatever the highest power is of that repeated factor, you would have to set one up for each of those powers. So if it was repeated 3 times, so you had this factor on the bottom that was to the third power, I'll just write it like this. Let's say that we had P of x over this ax plus b to the r. Whatever the rth power is that it's been repeated to, you have to set up a distinct fraction there for each of those until you get to that power of r. Now the good news is we won't usually see them to like the 10th power, because then you'd have to set up 10 fractions for each of them, and that will be quite complicated. We usually see it maybe to the second, possibly to the third power, but not often more than that. So whatever this power is that this has been repeated to, so if the highest power it has is to the second, you're going to have to set up a fraction for the first and the second power and find those constants on top. In addition to whatever other linear factors you might have, you'll set up a fraction for each of them. So if this was to the third power, you'd have to set up 3 separate fractions, one for each of its powers. Okay, so that's an R, just to say in general, you have to go up to the rth power, whatever it might be. Yeah, whatever the rth power is. Sure. Linear. Yep, linear is the key word there. Yeah, the repeated linear factors can be written as the following. Okay, so we'll probably be more clear once I show you a picture of one here. What does this look like? Hopefully. Question? Yeah, they just asked me there. I just gave a general R, so it's to the rth power. So whatever R turns out to be, you're going to have to go up to that power, whatever it might be. You got to start with 1, 2, all the way up to whatever the power is that it's been repeated to. You know, if it's only the second power, you could stop there. So R is just the general power. Okay, so let's go ahead and look at example 4 that has kind of this situation. So this one is x squared plus x plus 1 all over x plus 1 squared and x plus 2. I'll write it a little bit bigger down here so you can see it. If you have poor eyesight like mine is getting there, this is what it looks like. Okay, so notice in this one the denominator's already been factored for us, so it's been factored into x plus 1 squared and x plus 2. Is this an improper fraction? What do you guys think? No. The power, or the degree on the top is 2, right? What would the degree on the bottom actually be? 3, right? X squared and an x makes x to the third. So the bottom degree is actually smaller. So it's not improper. I don't need to worry about long division. So the main thing I need to do in order to integrate this is to do partial fraction decomposition. So turn it into some simpler fractions that we can use here. So that's what we're going to do. So let's set it up and find those constants. The bottom's already been factored for me. I know there's an x plus 1 squared and an x plus 2. So these are two separate linear factors, but this first one has been repeated. It has been repeated twice, basically. So we call that a repeated linear factor, okay? So when I go to set up the constants and fractions for this one, here's what I need to have for the denominators, okay? So for this repeated factor, I need first to have one fraction with it to the first power, and then one with that to the second power. Okay, so that's what I mean by when it's repeated, you have to consider one fraction to its first power, and then another fraction to the second power, but that's the highest it goes, so I can stop there. But I also need a fraction for the other linear factor, which is x plus 2. So that's how we'll set this one up. Okay, so anytime it's repeated, you have to remember you have to have a fraction for its first power and then its second power. If it was to the third, then the third power as well. But luckily, there's only 2 here. Okay, so now I still need to go find these constants, right? So hopefully then I can integrate this. Hopefully, we'll see what happens here. Okay, so how do we get rid of these fractions? Remember from yesterday? Yeah, multiply by the common denominator, which is what in this one? It's just x plus 1 squared, actually, and then x plus 2. So we don't actually need 3 of them because 2 of them will allow each of those to cancel out. So you really just use whatever's here in this denominator is the common denominator. Okay. So in the first one, what's going to be left is just the x squared plus x plus 1, right? Those will cancel all out with the denominator. What's going to be left with a? Let's see if we can figure that out. What factors? Yeah, so remember one of the x plus 1s will cancel. So x plus 1 squared and x plus 1, one of them will cancel, but there'll be one left. So x plus 1 and x plus 2. What will be with the b? Only the x plus 2 and the c? Yeah, x plus 2 cancels and you'll have x plus 1 squared. Okay, very good. So now we're kind of to a similar point we did in the last couple problems, examples 2 and 3. So now we've got to go through and try to find a, b, and c. Okay, so what's a good number to plug in for x on this one? -1. Okay, so that's a good choice, right? Makes one of those factors 0. On the left here, that will make 1 minus 1 is 0, so I think I get a 1. This term, -1 plus 1 will be 0, right? The a term will be 0. The c term will be 0. The only term left will be the b term. b times -1 plus 2 is 1. That looking good so far? So what is b? b is 1. Okay, I like b so far. We know that numerator is going to be 1. What else should I plug in for x? -2. Okay, that makes the other factor 0. So let's see, that'll give us 4 minus 2 is 2 plus 1 is 3. And then what do we have here? So this a term is 0, right? That's going to be 0 because of -2 plus 2 making 0 here. So is b. The only one term we'll be left with is the c term. And what does that give us? -2 plus 1 is -1 squared. 1, right? Okay. So what is c in this case? 3. So c is 3. Okay, now what should I plug in? Well, we already did -1. It will give us the same results. Yeah, it's like I've plugged in -1 and -2, right? And those are the two that make it 0. So I still need to solve for which one? A, right? So I can, that's the only one I have left. Since I only have one left, I could choose an arbitrary x now. So what's an easy x to plug in? 0. Okay, always a good choice, 0. So once I've made these zeros, I'm going to just pick one more, an easy one, like 0. And what I get on the left then is 1, right? What will I get with the a? It will be a times 2, right? 1 times 2 is 2, so 2a. B times 2, right? 2b. And how many c's? C times 1 is c. So I don't get any of them to cancel out. I get 2a plus 2b plus c. But Can I still figure it out? Sure, because what two values do I know now? B and C. So I can plug in B and C and then solve that for A. So the nice thing is I've already solved for these two. I'll substitute those in, and then I'll have A to solve for. So B is 1, so that's just a 2. C is 3. So that makes 5, right? So subtract the 5 to the other side, you get negative 4. So A is negative 2. So sometimes that happens in these repeated linear factors. You might only have two values to plug in, but a third variable to solve for. So just pick something easy. 1 would be fine, but I like 0. 0 is always nice. And then you'll be able to substitute and solve for that third variable. Okay, so now we're all set. We can rewrite our integral. We know the A, B, and C numerators. And hopefully then once we split them up into these fractions, I'll be able to integrate. So here's my new integral. So I start with A. A was a negative 2 over the x plus 1 to the first. The B was a 1, so plus 1 over x plus 1 squared. And C was 3, so 3 over x plus 2. Okay, so I do the partial fraction decomposition, break it down into 3 different fractions, and hopefully I can integrate these. Are you hopeful here? I think we can. These two are just ones we've seen before, right? Those are just natural logs here. How are we going to integrate this one? Can I? Yeah, bring it up to the numerator and use a power rule, right? So that shouldn't be too hard. So remember, when it's x plus 1 squared, I can bring this up and call it x plus 1 to the negative 2 and just apply a power rule. So now I should be able to. So this will give me negative 2, that's a constant out front, natural log of x plus 1. So when I apply the power rule here, what does this power become? X plus 1 to the negative 1. Anything else I need to do? Yeah, divide by negative 1 or put the negative out front. So remember, you just add 1, divide by the power. And then this will be 3 natural log of x plus 2 plus c. Yeah, so even though we have that, we know how to integrate. That's just a power rule. And we could do that without substitution as long as the derivative inside is 1. So we can do it like that. So when I'm done, I might just rewrite it a little bit here. You don't need to do much, but maybe, yeah, pull this out as a negative. Move that back down to the denominator. And then you can be done. So that's it. So once you get the partial fractions, hopefully then you can integrate those. A lot of natural logs, but if they have a different power, you can just use the power rule there. Okay. So questions on that one? Doing okay on that one? Okay, so just a reminder why we did this. When you have a repeated factor, something squared, make sure you set up a partial fraction for each power of that repeated factor. So to the first and to the second, and then any other linear factors, of course, need their own fraction. So that's what's important when there's a repeated linear factor. Okay, so let's go to case 3. So remember, case 1 was just all different linear factors. They each need their own fraction. Case 2 is some of the linear factors were repeated. Now case 3 is where we're not just going to have linear factors, but we're going to have an irreducible quadratic factor. So remember, what power does a quadratic factor have? 2, right? So this is going to have a factor in the denominator that has this x squared in it, and we can't break it down anymore. That's what irreducible means. It can't be broken down into smaller factors. So if that's the case, then how are we going to write it? So anytime we have now this fraction, r of x over q of x, and q of x contains this irreducible quadratic factor, I'll make a note of kind of what it looks like here. A lot of times that looks like this, like some ax squared plus bx plus c. So it has an x squared term in it, and possibly an x and a constant term. Might have one or the other or both. So that's what it looks like. And it can't be factored any farther is what that means. So if that's the case, then this will have a term of this form for the quadratic factor. So anytime it has a quadratic factor, what we now need to put in the numerator is the possibility of an x term. So if linear factors only have the possibility of a constant term on top, now a quadratic factor could have the possibility of an x term and a constant. Okay. So that's the difference when you have a quadratic factor. It could possibly have an x term and a constant term. And so when I set that up, I'll have to have two terms in the numerator. Okay. Okay, and with it, you will set up a fraction. If there's linear factors, you'll set up one for those. But this is what a quadratic factor will have in its numerator now. So one other thing before we go and do the next example with a quadratic factor in it. Question? Yeah. Yes. Yes, this whole expression will be part of the numerator, but it could have with it some other terms. If you have some other linear factors, let's say dx plus e, then we would just put another constant over there like c. Okay, so if it's just linear, it only has a constant term on top, but if it's quadratic, you have to set up two terms, one with an x and one for a constant. So linear factors in the past, we've only set them up with just a constant term on top, but quadratics could possibly have an x term as well. So that's the difference. No, the whole thing, well, you'll have more partial fractions, but that's what it would be for the quadratic factor. Yep. One other thing I wanted to mention is how we integrate another form that we're going to see coming up. So I'm going to go ahead and look at this for a minute. If you have the integral of dx over x squared plus 1. Does anyone know where that came from? Yeah, so remember 1 over x squared plus 1? Maybe you look at it in that form. That's the integral becomes the arctangent, right, or tan inverse. So I want you to remember that. That's the tan inverse of x. And we can adjust for it if this is something other than 1. So if we have anything where it's x squared plus a squared, it will become the arctangent. So this doesn't just work for 1, it can work for any constant squared. So I'll give you how we adjust when it's a constant besides 1. This becomes 1 over a arctangent of x over a. So if it is another constant besides 1, you do have to divide by that a outside and inside the arctangent as well. So we may see some forms like this where we have to integrate them because we're going to have these quadratic factors in the denominator. So those are two integral rules you can use here. When a is 1, of course, that's why this just becomes tan inverse of x, because the a's are both 1, but it works if there's a different constant too. Okay, so we might come back to that and use that here in a minute. All right, so let's go ahead and look at one that might have a quadratic irreducible factor down here in the denominator. So let's look at this one. Remember, first question you always ask yourself, is this improper, right? All right, a little bit bigger so you can see it. This one's x squared minus x plus 6 all over x cubed plus 3x. Okay, is this improper? No, right? Because you have a smaller degree on the top. So I don't need to do any long division, but keep asking yourself that when you get to your homework problems. So what I want to do instead is try to break this down into partial fractions. So to do that, I might think about how the denominator factors. So what can I factor out of the denominator here? X, right? And then what would I be left with? Yeah, x squared plus 3, right? Okay. Can I factor x squared plus 3 any farther? Not over the rational numbers, right? So, or even over the real numbers. So this is what I consider an irreducible quadratic factor. It has x squared in it, and I cannot break this down into smaller factors with an x. So this is what we consider linear, right? That's linear because it's x to the first, but this is quadratic. Okay, so it has a linear factor and it has a quadratic factor. Okay, that's different than what we've seen before. They've always been linear. Okay, so in order to figure out how to do the partial fractions or what the partial fractions are, let's set up this equation. Okay. Okay, so I'm going to break these down into partial fractions. We can do the x term first, it doesn't really matter, but the first one I need to do is for the linear factor x. So when it's linear, what do we put on the top is just a constant term. That's what we've done in the past, it's just a constant a. And we're going to go try to find what that is. Now I set up another fraction for the quadratic factor, x squared plus 3. But that doesn't just get a b on the top, right? What did I say it had to have? It has to have an x term, so a bx, and possibly a constant term, which is c. So that's right. So any quadratic factor has to have could have either a x term or a constant term or both. So those always need to set up two terms in the numerator. Okay, so linear factors just get a constant term. Quadratics get both an x term and a constant term. That's the main difference. So in 7.4, that's really what you need to remember. If your factors are linear, they get a constant on top. When they're quadratic, they get a constant and an x term. That's the difference. Okay, but you still got to go solve for both. So let's see if we can solve for these constants. Okay, what are we going to multiply by here? Should be, let's see, what? Xn x squared plus 3, right? Clear out the fractions, same way we've done in the past. On the left, you'll have x squared minus x plus 6. What are we going to have with our a term? X squared plus 3, right? Because x cancels. What are we going to have with bx plus c? X. So notice that you take the whole thing, bx plus c, make sure you write that in parentheses. That whole thing is going to be times by the x. Okay, so now we need to solve this out. So, how could I solve this? How am I going to get a, b, and c? X equals 0? Okay, let's start with that. So if x equals 0, the left side will be 6. This will be 0 plus 3, so 3a. And that will 0 this out, right? X is 0 makes that 0. So a is 2. What else could I plug in? Yeah, will negative 3 make that 0? No. So that's the problem with these irreducible quadratic factors. There's nothing you can plug in that makes it 0. So that makes it a little harder to solve because like now what am I going to plug in? So here's what we can do instead of figuring out a number to plug in, because we still have two unknowns. So we still have b and c, so it's going to be hard to just pick a value and get it to work out because there's still two unknowns. So here's what we're going to do. I'm actually going to distribute all of this through. Okay, so I'm going to distribute the a and the x through. Okay, so let's see what that looks like. That'll be ax squared plus 3a. What else? Bx squared, right? Plus cx. So here's an alternate way to solve this type of equation. One way is by plugging in values that make zeros in the factors, and that way zeros out and you get to solve for a variable. But that doesn't always work with the quadratic factors like this. So the other technique is to go ahead and distribute, even though it might not be pretty, and then match up like terms on the left and right hand side what their coefficients are. So for instance, on the right hand side, which ones have x squared with them? The a and the b, right? So a and b are with x squared. So I could factor the x squared out and call that a plus b times x squared. Okay, so a plus b is the same as the coefficient on x squared. The next term is the x term. I see there's only one of those. That's just a cx. And the constant term is 3a. And what I can do from here then is match up coefficients on the x squared, x, and constant terms. For instance, if a plus bx squared, it would have to match up to what coefficient on this x squared? 1. So what I know is that a plus b has to equal 1. Okay? This coefficient has to match to those. Those have to be equal because those are the only x squared terms you have. So that's the first thing. So could this help me solve for something? A plus b equals 1? Sure, because what do you know about a? 2. So now I can solve for b. Okay. So set the coefficients equal to each other and see if you can solve for some missing pieces. So subtracting 2, I get b equals negative 1. Okay. What does c match up to? Negative 1, right? Same coefficient. It has to equal the coefficient on this x, which is negative 1. So negative 1 is c. Okay, that's the only x term there is, so it has to have the same coefficient as this side. And we already know a, right? We already found a, so now we have a, b, and c. But the other thing you could do to find a would be to set up the constant term 3a equal to 6, and you could get the a that way as well if you didn't plug in at the beginning, and you would still get a as 2. So constant terms can be set equal to each other as well. Okay, so that's an alternate technique to plugging in x's, is distribute the right-hand side, match up coefficients, make them equal to each other, and you can solve for the constants that way as well. Okay, but I have all 3 of them now, so let's go ahead and set up our new integral and see if we can integrate this. Okay, so the first term a was the one that's over the x, so that was the 2. So that gave me a 2 over x. Now, let's go for this fraction. So this fraction is x squared plus 3 in the denominator. The b was a negative 1. So it's now a negative x is really what we have here, a negative x, plus the c, which is also negative 1. So it's like a negative x minus 1, basically. Okay, so that's my new integral. Okay, so I put that in for the 2. Both b and c were negative 1, so those both have a negative 1 in front of the x and a negative 1 that's constant. Okay, now the question always is, can I integrate this? Gosh, I hope so. Okay, so the 2 over x isn't going to be hard, right? But I see this fraction does not look that great. So I'm not sure, because if I do like a u substitution here, I'll get 2x. But the numerator has this extra term with it, and the negative 1, that's not going to really work with a u sub. But here's the thing you can do now that you have 2 terms in this fraction. You could split them up into 2 separate fractions. So now what I could have is 2 over x, and now I could put this negative x over the denominator separately from the negative 1. So that's usually how you're going to integrate, is when you get a quadratic factor like this, the 2 terms, by splitting them up. Remember, you can split up the numerator, just not the denominator. Okay, so now let's hope that I can integrate these. Can I integrate x over x squared plus 3? Yeah, this isn't too bad, right? Because you could do a u substitution. Because if you use the denominator x squared, then the derivative is 2x, and we have an x on the top. So that won't be too bad. What do you think I'm going to do to integrate this piece? Yeah, this is where the arctangent comes in. When we have 1 over x squared plus 1, it's the arctangent. We just have to adjust that this is a different constant here. This will be our a squared. So this form is usually an arctangent. So we'll usually be able to integrate it using an arctangent. So let's go ahead and do the pieces here. So we'll start with this one here. This first one is 2 ln of x. That's the easiest one. The linear ones are the easiest. Then we'll have this integral of x over x squared plus 3 dx. And you might need to do a u substitution here. So we'll do u equals x squared plus 3. And du is 2x. And you'll just have to adjust for the 2. So that shouldn't be too hard. So I'll do that one here in a minute. And then this one here, remember this is your a squared is 3, right? So this is the form for arctangent where a squared is 3. What is a going to be? If a squared is 3, a would be square square root of 3. Yeah. So this one will match up to the arctangent, and so this will integrate to 1 over a arctangent of x over a. Okay, so that's the formula for the arctangent. You just need to figure out what the a is, and it's always 1 over a arctangent of x over a. Okay, so I can integrate both of those pretty straightforward using a couple formulas. This middle one I'll have to do a u substitution, so let's see what that will look like. That will just be 1 over u du, which will give me the natural log of u. Okay, so I should end up here with 2 ln of x minus 1/2 natural log. I'll put the u back in, x squared plus 3, and then the arctangent. Okay. So that's how we'll integrate those pieces. This one you're probably pretty used to because we see a lot of linear factors, but this is really the two techniques we'll do for integrating when you have a quadratic factor in the denominator. Either a u substitution if there's an x term on top, that will usually work pretty well, or if there's not an x term, usually we want to try to hopefully put it in the form for an arctangent. And that's the case if you have 1 over x squared plus a squared. It will integrate to the arctangent. And it's always 1 over a arctan of x over whatever the a is. So that's the formula for that one. And then done. Okay. Right. You could make that square root 3 over 3, but I would accept this. That would be fine. Yep. I usually actually leave it like that so I know what a you had. So, okay. Questions on that one? How are we doing on that one? Yeah, so this one, just some new pieces about how we're going to integrate those. So those you might have to go back and say, okay, how am I going to integrate these pieces now that they have quadratics in the denominator? Okay, nothing right now? Okay, let's do one last case. What if we still have an irreducible quadratic factor, but it's repeated now? So repeated irreducible quadratic factor. So remember what happened when you had the repeated linear factor? You had to set up a fraction for both powers, right? When it was to the second power, you had to set up a fraction for the first power and the second power. It works the same way when it's quadratic. So they will need to have a fraction for all the powers. So this might look something like this. If you're looking for what this looks like, you might have this quadratic factor squared so that it's repeated is what that would look like. Okay. So then our fraction, r of x over q of x, will have these terms. Okay, so let's say we have this r of x is over some quadratic factor to the rth power. I'm going to use an r again. R just means that's the highest power it occurs to. If that's the case, then you have to set up a fraction for every power. And remember, quadratics always have two terms in their numerators. So you would start out with this to the first power, and then you would set up another fraction with it to the second power, and so on. Until you get to its highest power, which we called r, and then you can stop. Okay. But for every power up to r, you need a fraction for every single power, starting with 1, then 2, then 3, then 4, to whatever r might be, to the 10th. You'll have a fraction for every single power up to the highest it goes. Luckily, we usually don't go higher than 2. Maybe 3, so there usually won't be that many fractions. But you'll need to do that if it's a repeated factor, okay? Just like with linear factors. Okay, so remember, big difference between linear and quadratic is quadratics need two terms in the numerator. Linear just needs the constant term. So that's the big difference there. Okay. So let's try one like this. See what we can do for this example here. These are probably the most work because, of course, if you have multiple terms like this, you can imagine it gets pretty messy when you try to solve for the constants. So case 4 is really the hardest we will get to. No case 5. All right, so let's look at this one. This is x to the 4th. Let me write a little bit bigger for you. X to the 4th plus 1 over x times x squared plus 1 squared. That's the big version there for you. Next time I print it out, I'll have to make sure I make those bigger. The word's big, but not the integrals. Okay, so is this an improper fraction? No. Degree on top is 4. What is it on the bottom? 5, because this is squared is x to the 4th. Extra will make x to the 5th, so it's not improper. So I can't divide it out, but I see that I'm going to have to break it down if I have any hope of integrating this, because as it is pretty complicated. So it's already been factored for me, which is nice. So notice what we've got in the denominator here. What is the x? What type of factor is that? Linear, right? So this is linear. What is x squared plus 1? That is, yeah, quadratic, irreducible quadratic, because I can't break it down anymore. And it's to the 2nd power, so it's repeated, right? So this is called a repeated irreducible quadratic factor. So to set up our partial fractions, I'll do the linear factor first. So I'll set one up for x, and it actually doesn't matter what order you set them up in, but you got to do it for every factor we have here. So what does the x need on top? A. That's it, right? Linear factors only need a constant. So the next one, what do I need in the denominator for my next partial fraction? X squared plus 1, right? To the 1st power. So you start with it to the 1st power. What do I need in its numerator? Yeah, 2 terms, right? Because it's quadratic. So bx plus c. What does the next one have in the denominator? Yeah, x squared plus 1 squared, right? That's the next highest power is to the 2nd power. And then we can be done with that one. But what does it need in the numerator? Yeah, dx plus e. Just keep using the alphabet there. Or you can use other letters, but I just go down the alphabet. Okay, good. So linear factors have constants. Quadratics have 2 terms, x and the constant. Repeated factors, you got to always have first to the 1st power and then to the 2nd. Okay, let's clear this out. See if we can solve for A, B, C, D, and E. That's 5 things we got to find. Okay, so what am I multiplying by? X and... Exactly. X squared plus 1 squared. Basically, this denominator is the common denominator. So on the left, it will clear and just give you x to the 4th plus 1. On the right, with a, we should have x squared plus 1 squared, right? Because only the x cancels. What do we have with the bx plus c? It's going to be with that factor. X squared plus 1 of them cancels, right? But what else will be left? X, and what else? X squared plus 1, yes. All of that's left. Because only one of these canceled, you still have an x and an x squared plus 1. What's with dx plus e? Yeah, this totally cancels and you just have an x. Okay, so make sure those are in parentheses because you will maybe need to distribute there. Okay, what should I do now? Plug in 0? Well, that would at least give us one answer, right? So let's do it. So if x is 0, on the left I get 1. These 2 terms, this one and this one, will be 0. Because x is 0 makes that 0, x is 0 makes that 0. So I just have the a term times by 1 squared, so a is 1. So I've got a is 1. Something to start with. What am I going to need to do after that? Yes, because these irreducible quadratic factors, you can't plug anything in to zero them out, and you still have 4 variables to solve for. You're going to need to distribute and match up coefficients. So let's go ahead and do that. I might do it underneath here because when you distribute, it might be ugly, right? That's going to be a bit of algebra work. So x squared plus 1 squared, what is that? That's x squared plus, I know, x to the 4th, right? Plus 2x squared plus 1. If you FOIL that out, does that sound right? X squared plus 2x squared plus 1. And then you have to distribute the a times that. So this has to FOIL, and then the a is distributed. So you get ax to the 4th plus 2ax squared plus a. That's just for this piece. Now you've got to distribute all of this together. Yeah, that's not pretty, is it? You could do the x first, yeah. So maybe if you did the x, you'd get x cubed plus x right here. So distribute the x through to one of them, and then go ahead and FOIL what's left here. So let's see what I get. So I'm going to have bx to the 4th, that's that term. Outside terms are bx squared. Inside terms cx cubed. And then a c times x. Okay, so I distribute the x first, and then these two I just FOILed. Oh golly, that's getting long, right? Okay, at least the last one's easy to distribute. That's going to be dx squared plus ex. Okay, so let's go through and see. Yes, this exact one. No, I'm just joking. No, I don't think I did something with 5 variables. Maybe 4 will be the max here. But this might be on your homework, so we better go through how to finish this one. Okay, so first, let's see if we can get anything. I'll just start with the x to the 4th term. That's the highest, right? On the left, the power or the coefficient is 1, isn't it? What will it be on the right? What are the coefficients of x to the 4th on the right? A and b, right? So 1, this coefficient has to equal the a plus b. So I'll start with that. That's from x to the 4th. 1 coefficient here, a plus b there. And if it helps you, you could rewrite these in order, but I just don't want to write more than I have to, so I'll just pick them out of the equation. So if I know 1 equals a plus b, can I solve for anything? Yeah, because a was 1, right? So what is b? B is 0. I love 0 terms. That's a lot less work to integrate when there's 0. So 0 is good. Okay, so now I've got 2. I've got a and I know b. Okay, I can work my way down here. What is the x cubed term on the left? 0. What are the x cubed terms on the right? I only see c, right? Is that the only one with x cubed? I already used x to the 4th, so I'll cancel those out. I think that's the only one, right? So what does 0 have to equal? C. So c has to be 0. That's from the x cubes. All right, now I know a, b, c. What about the x squared power? What is it on the left? 0. What do we have on the right? 2a. I see a 2a plus a b, right? There's a bx squared right here, plus a d. So those are all from x squared. So there was a 2a, a b, and a d. Can I solve for something out of that? D. Because I know a, right, is 1. B is 0. So d must be not 0. What is d? Negative 2. Good. So the only one left we really need is e, right? And I see e is only from x. So what's the coefficient on x is 0. Do I have any other x's? Oh, I do. C and e, right? So 0 equals c plus e. So now I'm looking at the x terms. So this was from x to the 4th, in case you forget. This was from x cubed. This one from x squared. Now I'm looking at the x coefficients. So if 0 equals c plus e, what was c? 0. What does e have to be? 0. I love it when we get lots of zeros. Okay. All right, so here they are. A was 1, and d was negative 2, but the rest are 0. So I don't even have to put those terms in. which is awesome when you go to integrate. Okay, so let me set up my fraction back here. Okay, so I did have a was 1, so going back up, that 1 goes over the x, so I have a 1 over x. And then b, c are gone. So b and c, this fraction I don't even need. They're both 0, so I don't need that fraction. And then d had a negative 2, so there is a negative 2 in front of the x over the x squared plus 1 squared. So that's all I have left to integrate. All the other terms were 0. See, it didn't turn out as bad as we thought. We had 5 to solve for, but a lot of them were 0, so that's excellent. Okay, so how do I integrate this? Can I integrate 1 over x? Yeah, no problem. What about x squared plus 1 squared over 2x? Or with a 2x on top? U sub, I think, right? Because if u is x squared plus 1, there's the du right there. So I think that will work out. So let's do that in a minute. So a u substitution on this one. Make it 2x dx, so that should work out pretty well. So this will give us ln of x, and then I'll have this integral. I'll have a du over u squared. Does that become the natural log, that one? No, that's u to the negative 2, right? So you just use a power rule on that. So that becomes u to the negative 1 divided by negative 1. And then you can put in your u. So I should end up with natural log of x. This becomes a plus. This is basically 1 over u. So 1 over x squared plus 1 plus c. Okay. So after all that, it looked like pretty complicated to solve. We really ended up with 2 pretty easy partial fractions to integrate and got our final answer there. So that is a fun one, right? Okay, so now you've seen both methods in order to solve those. That's what you kind of have to do on those two. So let's see. I might have to stop for today because we're almost out of time. I didn't get to the very last one. It's really called rationalizing substitutions. So it's not the other cases. So let me see. We'll stop there for new stuff. I'll do that on Friday along with 7-5. We'll have time to finish that up. But I'll have to take a couple off of your assignment, which is, I know, devastating to you when you don't get to do all the problems you wanted to. Let's see. What problems are on there that are in the 40s and 50s? Any? Who has the list? Taylor always has a list. Thank you. I'll write the couple down that we can delete off of there. Okay, 47, 48, and what was the last one? 64. So 64 I think is fine because that's just the area under the curve. So 47, 48? Okay, got it. Yes, that's all from the last piece. So you said 39, 40, 47, 48? Okay, these I'm going to take off, so there you go, be a lot shorter. And I'll actually post that on Canvas this afternoon too, just to remind you. So you can delete those last 4 off of this part 2 homework, and I'll probably just put them as a separate assignment, do a little bit later after we finish those on Friday. So, okay, that'll be a little bit shorter for you. All right, I think that's it for today. Yeah, any other questions right now?